Yeah,
Okay.
please.
Yeah, let me start. So yeah, thank you very much for the invite. This great workshop for large language models and autonomous driving. We at Wayve started researching that topic actually about 1 year ago, and already tried different things. And just wanted to start with a small introduction because at the beginning, when we started that, many people wondered why would one use large language models for autonomous driving, and we kind of now we finally understood why, and have several arguments for that. So Wayve, as opposed to a classical self-driving company that consists tries to solve self-driving using multiple components in perception, planning, and SLAM. Instead of that, we use a neural self-driving stack that consists of one big neural network that we train end-to-end. We pretty much just take a camera input and a few other sensors like GPS and radar. So it's a very lightweight sensor stack. And just feed it raw into one big neural network, which outputs motion plan that is fed to the controller. And that's pretty much it. And did we pick with this approach? So Wave started that about 6 years ago, and this is all falls down from this thesis of software 2.0, where if we use end-to-end systems, those systems would be computationally homogeneous. It's very simple to bake them into silicon, so they're hardware friendly. They have other nice features like constant running time. So there are no really surprises in terms of performance on board. Another feature that not many people highlight is agile development at the company that you can achieve if you use this approach, because now instead of multiple teams working on multiple components, you just can have one single component, so a single person can understand the whole stack pretty much, which is impossible in regular self-driving. Then research and the engineering has really nice interface boundary, which are just neural network weights that could be shared. So then code bases between research and development could be split, and so on. But mainly people are excited about neural networks because it's supposed to offer superior performance and outperform human coders, which we started seeing in the recent advances in the AI. So this is a demo of our car. Hopefully video plays well. This is just a sped up video in a central London where a car takes on different narrow roads, let drivers pass, and so on and so on, takes all the turns past pedestrians, while never been explicitly taught what is a pedestrian or a car, because the whole model is trained, as I said, end to end without any segmentation or object detection. And specifically, well, recently we started to see new emergent behaviors that, again, we didn't teach the model to do, but it just does it by itself from our end-to-end training. So for example, at the bottom, you can see that the model ignores the newspaper on the road on the bottom left. But on the bottom right, it decided to avoid this garbage bins, black garbage bins that were tipped over. And again, I want to emphasize that we don't have any concepts of newspapers or garbage bins and so on and so on. So this is just purely based on either human demonstrations or other techniques that we use. And on the top, you can see that it can navigate very narrow intersections and narrow gaps in traffic, different protected turns, slow down on speed bumps and things like that. So we can clearly see these new emergent behaviors from end-to-end training. But there are limitations to AV kind of 2.0, like how we call it, or end-to-end AV. So the whole model is a big kind of black box. And it's very hard to debug and explain what it's doing. So effectively, the model takes just multi-camera, multi-step video input and other data from the car, like speed and steering wheel angle, and produces this motion plan. And everything that happens inside is kind of a mystery. So that's always a problem with such big models. Also, feed-forward networks that we can use for such policy networks scale poorly with respect to input and output temporal length. And in self-driving, we don't really know exactly how much time we need for how much input should be memorized and how long in the future should we plan. For example, you can have a case where you see a traffic sign and then you immediately get into traffic jam for several minutes. So you better remember that traffic sign that you just seen, and so on and so on. So it's actually like a very complicated research question. How can you add memory to very long memory to end-to-end systems? But also it's a research question. How can you do planning and predictions in such systems in a scalable way? How to add common sense into such systems? And yet another challenge is how can we quickly change the behavior of the policy? Because if you use component models, you can tune the heuristics, you can change some rules, but it's very hard to retrain such networks. So it would be great if you can just change rules and add few edge cases without retraining. And the main limitation, obviously, for all end-to-end systems is that we need a lot of data. And data is expensive. So, for example, human supervisions that have car trajectories are very expensive. But the most precious is this edge case data, which you can see on the road, which consists of novel combinations of objects, like you can see where a road is just kind of reflected in a shiny truck, or rare objects, or people just being creative on the road. So at the bottom, you can see those like traffic cones, people in Halloween dresses, right? So the car should uh, understand that those are not regular traffic cones. And as a humans, we kind of know that it's not that we supposed to just assemble a huge data set of Halloween costumes in this case, is that we just need to reason about the scene. We need to understand that, okay, well, those are people, and it's probably Halloween, and we should be careful about them. They're going to be walking and so on. So this explicit verbal reasoning is what humans would use in those situations, as opposed to a lot of expensive edge case data. And response kind of solution to all those problems would be we found that generative text and video models actually solve many of those issues. So, for example, you can train to predict a video that would be a very cheap unsupervised data that you can get without actual trajectories. You can add common sense using pre-trained large language models, because they in turn are trained on this huge internet scale text data. And we all know that GPTs recently been shown they have emergent reasoning capabilities. They can do few-shot learning that is nice for like changing rules. And for planning, we can use autoregressive video world models that I'll show later. And again, obviously, all those ideas also give you a lot of explainability. So, for example, we can interrogate the deep model with a video question answering, or just generate video from the model to see if it understands the environment. So at Wayve, we have two projects addressing that. So Lingo is a video question answering model, and Gaia is a video generation model. Both are big transformer models, whereas in one case, Lingo takes in video and chat with the user and kind of autoregressively predicts the responses, like a ChatGPT would do, except it takes in video as well. And Gaia is kind of inverse of that, where it's a text conditioned video generative model. So it also takes in, it could be conditioned on a video or on some text, and it produces text. It produces video instead of a text. So I'm mainly going to focus on Lingo in this workshop since it's about LLMs, and maybe have a few words about Gaia at the end. All right, so Lingo is a video QA for self-driving. So we decided to start with the explainability for self-driving, specifically addressing several explainability issues. We can ask questions about perception, counterfactuals, planning, different road rules, and where would driver pay attention in a specific driving scene. So for example, you can ask, what's your plan for the next 3 seconds and why? And the model is supposed to respond that I'm slowing down because there is a van merging in my lane or something along those lines. So here's a demo of our system that we put on a blog recently. So I can read here if you guys can see. So what's the weather like? It's raining. Do you drive differently in the rain? The model says, yes, I need to be more cautious due to the rainy conditions. And how user says, how come? Due to the rainy conditions, the road might be slippery and visibility might be reduced. So you need to drive more cautiously. When will you go? I will go once the black sedan in front of me starts moving. So it's kind of understands the scene. When will it stop raining? And this is just a regular chit chat kind of. I cannot predict when it will stop raining. Is it true that it always rains in London? No, it's not true. It always rains in London. However, it's known for its rainy weather. And this is just a kind of generic reasoning. And just to prove that it's not always raining, this is a sunny scene. Why you stopped? I'm stopped because the traffic light is red. What are the 3 top hazards that you're paying attention to? The model says the top 3 hazards I'm paying attention to are the traffic light, the cyclists in front of me, and the pedestrians crossing the road. Why? I'm paying attention to these hazards because they can impact my safety and the safety of others on the road. When can you go? I can go when the traffic light turns green. So it kind of understands everything about cyclists here and the traffic light. So now just a few technical details on how we train those models. One specific issue that we worked recently quite a lot is a video QA evaluation. So what we want is to evaluate the video QA performance that is correct, robust, cheap, and mainly fast. And you can see that, imagine that you need to automatically or not automatically evaluate the following response. So for example, you can ask, what are the top 3 hazards you're paying attention to? And the model responds with kind of a bit lengthy but factual sentence, like the top 3 hazards I'm paying attention to: a traffic light, cyclist, etc. So you can see it's kind of quite hard to automatically understand if such an answer correct or wrong without looking at the video, even having a label, because, well, obviously looking at the video will defeat the purpose of automatic evaluation. So yeah, we found for practice that evaluating free-form text is extremely hard problem. So human evaluations are prohibitively slow and expensive, so you wouldn't be able to run them on a regular basis. We also investigated in the classical n-gram-based metrics like CIDR and BLUE that compare the different text responses and found that they're not quite robust, specifically in self-driving scenarios where a single word like left or right can be of a big difference, or traffic light being red or green is a big deal in a long sentence, but such systems wouldn't pick up this single word difference correctly. And also recently, LLM-based evaluations became popular, like asking ChatGPT or other LLM model whether something is correct using just API. But we found that this is very expensive and slow as well, because you want to ask very powerful model like GPT-4 to evaluate your questions. So what we did, we came up with this trainable evaluation pipeline that we call Lingo Judge. The way it works is that first we feed a video snippet into the Lingo model, which is this big LLM video model. We also ask a question, and the model generates an answer. Then we feed the generated answer, the question, and the human answer, so just text, into a smaller uh, trainable model. It's also an LLM, except not so large, which we call a judge, that in turn we train to predict the correctness score from 0 to 1. Specifically, we used the BERTA v3, a fine-tuned model using LoRa. It's about 180 million parameters with a linear head on top. And we designed a data set about 4,000 question-answer pairs such that we can train such model. Another kind of idea that we put that boosted the performance of such system is to use max operator and several responses between several human ground truth responses, such that we compare the model's answer to one of them and just to, for example, use only one of them. For example, in this case, you can see that the question is, are there any pedestrians crossing the road? And if yes, how many? And the predicted response at the bottom is, yes, there are 2 pedestrians crossing the road. And the human ground truth is one of them, 2, one close to the car, one further away. And another one is a longer one, which is also kind of says that there are 2 pedestrians, but in a long manner. And after calling Lingo Judge to compare those performance, Lingo Judge says, okay, well, the first one matches and the second one doesn't. And that is good enough because matching just with one ground truth is already means that the question answered correctly. So we just go and say that the correctness of such responses in this specific case, 0.94. After having such automatic evaluation, we also graded many models, like a dozen of models with just ourselves and using human graders. And after doing so, we can start plotting these correlation curves where we can plot human grade to the model. So every point here is a model, and they evaluated by humans. So we can plot automatic metric like a Lingo Judge, or at the bottom, ChatGPT, GPT-4 specifically with chain of thought prompting, and a human grade, and build this correlation curve just to understand how well the metric correlates to human judgment. And we found that such trainable neural evaluators have great correlation with human judgment, even slightly better than expensive GPT-4 with chain of thought. This is kind of our best shot on using off-the-shelf LLMs. But at the same time, being considerably faster. You can see on the right column that the time to evaluate on a whole validation set is only 10 seconds for the judge, for the Lingo Judge, and 3,000 seconds for GPT-4V. So, which means that we can run such evaluations right during training. For example, we can build training curves using actual VKA ground truth, which is extremely valuable for the research and just boost the team research cycle because you don't have to wait for your evaluations and can just immediately, finish the jobs and do the ablations and so on. All right, so some details how we train it. So we use the many different data sets, academic data sets, a lot of some manually annotated data sets through annotated by ourselves, so contractors, then try to boost the performance with preference learning through our LHF and so on. One of the very interesting thing we found is it's very productive to have auto labeling pipelines where you can use some metadata and short annotations from humans that we have for our driving runs, and then run them through rephrasing LLMs, and from that have just a video QA sample. For example, you get this video, you collect some metadata, and then you can ask questions through LLM. Sorry, you can generate questions and answer using LLM. For example, what is the traffic of the light? Traffic light shows green. What action are you doing? And so on and so on. So by that, we can collect a lot of data. And want to advertise that soon we're going to release some of the auto-labeled data sets for the community. So just stay tuned and just check us out on a GitHub, on the company GitHub. We will just release it shortly. So specifically, we will release about 420,000 QA pairs for different with video snippets. And obviously the evaluation data set, which is very, highly curated 1,000 hand-labeled QA pairs with video clips about action, justification, attention, localization, and so on, object localization, and so on, together with Lingo Judge, so the community can evaluate video question answering pairs. And by the way, for the reference, our best model trained only on the second public, soon to be public data sets achieves 60.8% of accuracy, according to the judge. So there is some room for improvement, but it's kind of a nice baseline. And having those automatic evaluations, we can ablate many different options. For example, here I just pick some interesting ones. So one of the, since fusing video into a large language model is a novel research subject, not many people are doing so, mainly using some kind of metadata. We researched many different ideas. How can you use that? We decided to focus on BLEEP2 inspired architectures as opposed to Flamingo with cross attention. So in BLEEP2, you actually take frames of the video and generate tokens out of them. And we try to use different fusion models for this such token generation. It's kind of probably not enough time to go into details, but we found that late fusion and mid fusion, where you try to where you generate kind of quite many tokens from your frames is the best. Whereas if you try to fuse video early, kind of reducing probably the information getting that gets into LLM, you get inferior results. Few kind of a small slide on training setup that we discovered to be the best. What we do, we first pre-train our system on generic video and image QA data sets. Specifically, we use GQA and Suite and few others, SVIT, which has about 26 million QA pairs. We train pretty much everything in such a model, and we kind of discovered that tuning attention is a nice trade-off between parameter efficiency, because tuning with LoRa is a bit inferior, although faster, but fine-tuning the whole large language model, it's not so practical. So tuning just attention we found to be the most practical and leading to best results. In the second step, we fine-tuned such pre-trained system on actual self-driving video QA pairs that I showed. We also did a bit of ablations on which LLM you can use. And one interesting result here is that matching parameters late. So even if you match a number of parameters in language models you use for the backbone, as expected, you find that recently trained LLMs behave way better than older OPT models that was used originally for BLEEP architecture. Also, probably a bit surprising that advertised Mistral model performs a bit worse than Vicuna model, which is a bit older, at least in our settings. Okay, what are the next steps for Lingo? The main limitation of all of that I presented, this is video QA explainability. So which means that the model is really like a backseat driver. So there is a actual driving model that takes decisions, and there is this other model that tries to explain what another person is doing, kind of another robot is doing. And a priori, it's not obvious that the explanation would be matching to what actual driver is acting on. So what we started researching on is how to ground the actions of a model to the explanations, and in that case, we can feed trajectories that a driving model generates, or even generate our own trajectory to this big multimodal system that takes in now video, text, and actions, and also can generate text and actions in response. And a kind of sneak peek preview is that we started testing such a model in a closed loop settings in our nerve neural simulator. So here you can see probably one of the first in the world large language models driving a car in a closed loop in a neural simulator. So far, I was not aware of such things. So stay tuned again for updates on that. All right, so a few words about Gaia video generation model. So video generation from deep models is a quite novel area of research, and recently several teams started applying it in self-driving. So high level Gaia works as following. So you can read about this in a report that the Gaia team posted recently. But the way it works is that first it tokenizes the video, then it predicts in this latent kind of token space future kind of future frames on a low rate, and then there is a video decoder, which was one of the main innovations of the Gaia team, that can decode very smooth and realistic videos out of those predicted tokens. So at the end of the day, encoder and decoder are different, and that allows to generate very nice videos out of the model. Specifically, decoder can do different multiple tasks, so you can just decode. It's a big video diffusion model, so it can decode, but it also can decode just frames. It can decode videos conditioned on previous frame, but also very importantly can interpolate frames leading to high FPS videos. And we found that, as usual, it scales very well with a number of parameters and data used, and all data is self-supervised. So here are just a bunch of snippets of videos generated by this model. You can see that they're pretty much indistinguishable from real videos. If you just pay very close attention, you can see that some objects are a little bit morphed, and sometimes they appear a bit unrealistically, but if you just squint your eyes, there's no way you can tell that those are not real videos. And the main feature that the Gaia team achieved is that they can generate very long and stable scenes. So here you can see videos that go on for minutes, for even I forgot what's the max time they got generated, but you can see that it's a cohesive scene that kind of goes on and goes on, and cars emerging and pedestrians and so on and so on, and it doesn't degenerate into some kind of noise that many video models can degenerate to. And one specific feature it can do is conditioned future sampling, where based on certain latents, it can pick a different future from a original kind of video conditioning. So in the first case, on the left, it goes straight in on the intersection. In another sampling scenario, it goes right, which can be used for planning. Gaia is actually text conditioned as well, so you can generate. So here's the example where we use text for conditioning for generating different weather conditions. So you can see that it generates rainy and snowy, which is kind of rare in London, but still happens. Foggy and so on. So yeah, as a conclusion, we found at Wayve that generative AI can close this gap, remaining gaps in AV 2.0 and end-to-end self-driving. Specifically, a large language model can solve explainability and eventually reasoning and planning for end-to-end self-driving, and video generation will help solve prediction and again kind of research like planning for our future models. And one interesting thing at the end of the day, all those models are just big scaled up sequence predictors. So hopefully we will be able to merge all of that together. All right. Yeah, I think I'm out of time. So yeah, thanks a lot for your attention.
Thank you. All right. Thank you, Dr. Sinavski, for his awesome talk. So do we have any questions here in the audience? So please try to use the mic.
Thanks for the nice, wonderful talk, Dr. Sinavski. And I have two questions. One question is for the first Lingo QA dataset. And the current very popular dataset is New Scene QA. What's the difference between the Lingo QA and New Scene QA? And the second question is that for the Gaia for video generation, and the Gaia is trained in London city dataset. What is the model generalization capacity while we apply it for other cities? Thanks for the wonderful talk.
Yeah, thank you very much for the question. So as for the first question, so New Scenes QA, yeah, we are aware of that data set. So first of all, there are several limitations that we kind of so first of all, we as a private company obviously interested in dealing with London data at this point because we're trying to deploy self-driving in London. Hence, out of necessity, we have to deal with data distributions which happen to be in London. So hence, we decided to pursue language generation and so on those London data sets, obviously. Second is, so actual technical differences with New Scenes is that one kind of nice thing for research is that we provide a single camera video QA, which is very fast for a research iteration, right? Because actual New Scenes, you can, to the best of my understanding, I think they use 6-camera setup, which is quite challenging to run initially for like just kind of researching different ideas. Yeah, and then additionally, we again trying to contribute to the community, so we're trying to release yet more data for everyone else. So it's on top of New Scenes. So it's yet another argument for extra data set. So yeah, and another thing is that we're going to release the evaluation methods with a judge, and to the best of my knowledge, in New Scenes it's not released. It's not built. So the second question, again, very similar to the first one, we are focusing on cities where we're going to deploy our systems. Hence, so far Gaia focused on the London data sets. And specifically, one specific thing about London, it's a left-hand driving city, which is not so frequent, right? There's a few other, obviously, countries that do that. But yeah, this is like a big thing for us to work on a left-hand driving data sets as well. And to the best of my knowledge, so far we haven't tried to apply it to other cities.
Thanks.
Thank you.
Thank you for the great talk. I have one question. Both Ringo and Gaia 1 use a big transformer architecture. And I think in Wave, you plan to run such a transformer model on edge device in real vehicle. But for now, there is no accelerator for transformer architecture. And my question is that, do you have any strategy of running such a big transformer run in edge device?
Yeah, we have several strategies actually that we're going to pursue. We'll see which one will work out. Yeah, can't really go into like much details. Just want to say, so first of all, we can notice that from the time GPT-3 appeared, which was pretty much last year, this time, right? So it's like 1 year only passed. We can see that 7 billion models like Mistral and a few other models can match that early GPT-3 model, GPT 3.5 Turbo, that became Turbo model, in terms of reasoning and a bunch of other things as LLM. So you can see that in 1 year, we pretty much dropped the number of parameters from 175 billion to 7. And you can see that many people working on pruning it more and more. For example, recently Microsoft released Phi, which is a 1.5 billion parameter model. So there is just a tendency for, I feel like the whole humanity will at some point figure out a smaller one, which would be good enough for our purposes. This is one thing. Another thing is Wayve is, again, the whole idea of the company is to bet on deep learning in the cars. So we have our proprietary kind of systems to run as large models as possible. So this is kind of our bread and butter. We are running large neural networks on the car. So we have several implementations where we can, use it. And again, you can see that other developments in the field like flash attention 2 and speculative decoding and KV caching and so on, they just keep speeding up the inference time, because here we just need to speed up inference, not really the training. And again, this is yet another avenue that we kind of researching in. Yeah.
Thank you.
Any other questions? All right. Okay. So thank you again for joining us, Dr. Sinavski. It's really a wonderful talk.